So next question asks, if A and B are both countable, then A cross B is countable. And this may seem a little bit unintuitive because A cross B is much bigger than A and B, but let's try to break this down. So one intuition is that pairs of this form look like things of the form AB. And so we know for a fact that because we have a bijection, because we have bijections F that takes A into N and G that takes B into N, we can sort of define a new bijection that takes AB to F of A and G of B. So this is basically saying, let's take the pair A cross B and return to like N squared, just by sort of translating A to a natural number and then separately translating B to a natural number, which we know we're allowed to do freely. And so what we can notice is that these look like pairs in N squared, and these are pairs of natural numbers. And we can then say, oh wait, let's just do something that then takes like this thing and turns it into like F of A over G of B in Q. And so, because essentially we've said that, oh, an ordered pair of A and B is equivalent to an ordered pair of integers, which is equivalent to a rational number, because a rational number is ultimately a pair of two integers, m and n, just divided. And so we've essentially created a bijection between this set and Q. And we know that Q is countable from the notes, and therefore the set of A cross B is countable, since we could then imagine another bijection from like Q to N. So the next question sort of builds on this idea and asks if each individual AI is countable, then is any finite product of A's countable? Or yeah, is any finite product of A's countable? And this is something that turns out to be true. And fairly straightforward way to see it is being like, oh well, A1 cross A2 is equal to, let's call it like A12, is countable. So this reduces to like A12 cross A3, AN. So this is a product of n minus 1 countable sets. And again, we could group these together and sort of collapse it down. And so this is an intuition for why it holds, and a formal proof of this would pretty much be an induction of noting that it holds in the base case of A cross B, and if you do A cross B cross C, you can collapse A cross B and turn that into a countable set times countable set, which reduces to your base case of 2. Ultimately, the formal proof isn't super interesting, and it's just like a bunch of window dressing around this idea of like, we can collapse, anytime we see two of them together, we can collapse them down. So yeah. So the next question. You would initially hope that this is true, but the trick is that because the previous proof relied on induction under the hood, we can only use it for any finite n. Because in order to repeat the induction up to a number, you need that number to be finite. And so if you have it, even if it can be arbitrarily large, but it must be finite. But here, if you have an infinite product, you cannot use the induction. So you can't say that it's countable using that proof. Although it may still be countable, we need to show that it isn't. And so the idea is that this turns out to be false. And one way to see that is by saying let AI be the set of like 0 through 9. So just our space of digits. So then you can, so the infinite product of A1, A2, and so on, if we do an infinite product, we can represent infinite length numbers in here. And indeed, we can represent all of the real numbers because every real number is just an infinite length string of digits. And so we're saying that, well, this thing has enough space to hold real numbers, which is uncountable, and therefore must be uncountable. And the interesting thing here is that AI was not merely countable, but finite. So even if you take a finite set, if you do a countably infinite product of it, it turns out to be infinite. Yeah. And so that's the thing. That's a warning of like, it's important to keep in mind the subtleties of induction, and you only use it to prove things for like finite cases, and it doesn't always generalize to infinite cases as well. So be careful. The last one is asking that every infinite set that contains an uncountable set is uncountable. And we actually saw a version of this argument early on in part A, where we said that if X subset of A is uncountable, but A is countable, then we have a bijection that takes N into A. But then we also have a bijection surjective from N onto X. And so because we have a surjection, so N, we're saying that for every element of N, we can map it to an element of X, even if it's not unique. We haven't necessarily shown uniqueness, but just showing that a surjective is enough. So because we have a surjection from N to X, we can say that the cardinality of N has to be greater or equal to the cardinality of X. But this is uncountable, and this is countable. So we have a contradiction. And so ultimately the statement must be false. And this is in line with our intuition, which is that if you contain an uncountable set, you must be at least uncountably big yourself, because you have an uncountable set inside of you, and therefore you can't be countable. So yeah. All right.